So today we will discuss helimagnetism or helical magnetic ordering. Ferromagnetic alignment
of atomic moments within the layers, okay, and the interaction between layers, it can be described by a nearest neighbor exchange constant J1 and next nearest neighbor exchange constant J2. Okay. Okay, chalo. So now if the angle between the magnetic moments in successive planes is, let's say, theta, okay, then the energy of the system can be written as E equal to minus 2n s square J1 cosine of theta plus J2 cosine of 2 theta. Okay, so n is basically number of atoms in each plane, okay, and s is of course the spin. Okay, so here basically individual layers, so these layers, okay, they are coupled to each other via an exchange interaction, and this interaction is determined by two constants. So one is J1 and J2. So J1 is nearest neighbor, okay, and J2 is next nearest neighbor, okay, and the energy corresponding to that is written like this: 2 minus 2n s square J1 cos theta times J2 times cosine of 2 theta. Okay, ठीक है? Okay.
Hello, sir.
Yes.
Yeah. So here we are taking J1 and J2. So what about other neighbors? It is a little bit farther from the first one.
Good
so
question.
They will be.
Okay. So the thing is that, of course, in principle, you should be considering other layers also, but maybe that interaction strength is not that much strong. So basically, effectively, after the next nearest neighbor, it doesn't contribute much or doesn't make much of a difference. So probably that's why we are not considering it. Okay.
Okay, sir. Okay.
Because like next nearest neighbor, the distance will be quite high, right?
Yes, sir.
Okay. So you need to think it like this. Okay. So let's say 1, 2, 3, 4, 5, 6. I have something like this, right? Okay. Now let's say if this one has a nearest neighbor interaction, so it will interact with this and it will interact with that, right? Yeah.
Yes, sir.
If it has next nearest neighbor interaction, then it will interact with this and then it will interact with that. Okay, right? So as you see, compared to nearest neighbor, next nearest neighbor is already at a larger distance. Okay. Now let's say if I want to have next nearest neighbor, okay, so it will be somewhere like here and somewhere like there, right? Okay. So basically
Yes.
what we are talking about is this guy interacting with this guy or that guy, right? Sorry, not that guy, but let's say that guy, right? Okay. But if you look at this is already somehow kind of like considered here, because this guy is again interacting with this one and this guy is again interacting with this one, right? So in principle, this guy is talking to this guy already via this and this, right?
Yes, sir. Yeah.
Right. So in a way, basically we are not completely ignoring, but basically this part is already considered somehow in the other one. Or independently, if you say, then I think this is already will be at a much, let's say, lesser, what can I say, like the strength is quite smaller compared to the other two. Okay. So that is why we are not separately considering it. Okay.
Yeah. Thank you.
Okay. So now let's say if this is the energy, so now this energy will be minimized when del E del theta will be equal to 0, right? Okay. So now if we have this, then what we can do here is we can apply this. So if we do del E del theta, then what we will find here is that, so basically this E we have, and then this is my, let's say, equation number 2. Okay. So if I do del E del theta, so then what I'll find is that J1 plus 4J2 cosine of theta times sine theta will be equal to 0. Okay. Now the solution is either sine theta is equal to 0 or cos theta equals to minus J1 divided by 4J2, right? Okay. So if sine theta is 0, that means we have two possible solutions. Either theta is 0 or theta is pi. Okay. Right. So if theta is 0, that means it will be ferromagnetism. And if theta is pi, then this will be antiferromagnetic ordering. Okay. So this other solution, what it gives us is something other than ferro or antiferro. Okay. So this solution corresponds to helical ordering, also known as helimagnetism. Okay. Okay. So let us now see what exactly happens here. Okay. So let's say just give me a second actually.
In the bracket, it will be minus J1 square by 4J2 minus J2.
Okay, very good. Correct. Okay. So we have got the energies of these three configurations.
Sir, 0 is for for the parallel spins, no? Like if the exchange spins are parallel, then it will be ferromagnetic, and if they're anti-parallel, then they're antiferromagnetic. And in between them, it will be helical, as you said.
Clear now?
Yes, sir, clear.
See, I've drawn here the vectors. Okay, so what is theta? Actually, this angle between vectors in different planes. Okay, so as I move across different layers, so basically from one layer, if I'm going to other layer, which is basically the thickness. Okay, is this part clear? What I wanted to say here? Okay, let me draw it. I'm not sure. Okay, so suppose I have a material like this. Okay. 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 So let's say this is my thickness. Okay. Now what I'm saying here is that there are this is made up of such layers. Okay. Is it clear? Okay. And the magnetization vector in this layer is, let's say, like this. Okay. Okay. In the next layer, it rotates by an angle, let's say theta from this. From this to this, it rotates by another angle theta. Okay. From here to here, this is again theta. So basically, this rotation in successive planes is theta. Is this part clear? Abdul?
Yes, sir, clear.
Okay. So now if theta is 0, that means this line will be again following on the same, right? This line will also come here, right? Which means that each are kind of lying parallel to each other, right? So this will be a ferromagnetic kind of thing. And if it is 180°, then let's say one will be like this, other will be like that, right? This one will be like this, the other one will be like that. Okay. So effectively we will get a antiferromagnetic kind of order. Okay. Clear?
Yes, sir, clear.
Okay, chalo. Okay. Now what we have done here is that we have estimated the energies in different configurations. Okay. Okay. So now let us look at the phase diagram. Okay. Okay. So let's say this is J1. Very bad. Okay. Let's say this is J2. Okay. So here okay. So let's say this is my kind of invisible boundary. Okay. So here on this J1 and J2 plane, here we will get a ferromagnetic ordering. Here we get antiferromagnetic ordering. Here also it will be ferromagnetic. Here also it will be antiferromagnetic. Okay. And in between these two dotted lines, this part will be helimagnetism. Okay. Is clear? Okay. Okay. So helimagnetism is favored over ferromagnetism and antiferromagnetism when J2 is less than 0 and mod of J1 is less than 4 times mod of J2. Okay. That it has to be ferro. If
then
J1 is
we are-
negative, okay, let me ask you a question. If J1 is negative,
Huh.
then what do you expect?
Yes, sir.
If the
Then
exchange
it will-
integral is negative, what do you expect?
Exchange integral J is less than 0. That means total energy positive.
Don't
Antiferromagnetic.
go to total energy. Simply think of, you have, let's say, in Hamiltonian SI dot minus J SI dot SJ. It's okay. Huh?
Yes, sir.
So if J is greater than 0 or J is less than 0, what do you expect?
Sir, for greater than 0, ferromagnetic. For less than 0, antiferromagnetic.
Does that answer anything?
Sir, because it depends on total energy now.
Total energy is something that you are calculating.
Sir, I'm not getting here how you are doing that. This one is FM, this one is antiferromagnetic in this phase diagram.
Yes, so for that, what you have to see is that you have to find out different conditions. Okay. And okay, so you first solve this problem, then I think a lot of things will be clear. Okay, so let me tell you anything. Okay, so let's say in the first quadrant you have J1 and J2 both positive, right? In the second quadrant you have J1 is negative, J2 is positive, right? Yes?
Yes, sir.
And then in the third and fourth quadrant you also have similar kind of situations, right? So
Yes,
you have
sir.
to put these conditions separately, and then you have to see which one of these three configurations have the lowest energy under such circumstances.
Okay, sir.
Okay.
Yes, sir.
So that will then tell you basically which quadrant will have ferromagnetism, which quadrant will have antiferromagnetism, things like that. Okay.
Okay, sir.
Okay. So maybe you
Yes,
can
sir.
try it as an exercise. Okay. But let's say first
Yes.
you try this, then maybe you can do that. Okay. So here this helimagnetism is favored over ferro and antiferro when J2 is less than 0 and J1 is less than 4J2. So you have to prove that. Let's
Okay,
say
sir.
this is my quadrant 1, right?
Yes, sir.
This is Q2, this is Q3. Let's say this is Q4. Okay? Right? Now, let's say in Q1, what do we have? J1 is greater than 0 and J2 is also greater than 0. Right? Okay.
Yes,
Now let
sir.
us go to the expression here. So EFM is minus 2n square J1 plus J2. Okay. So EFM is minus 2n square J1 plus J2, and EAFM will be minus 2n S square minus J1 plus J2. Okay, minus J1 plus J2, right? Agreed? Okay.
Yes, sir.
Okay. So now I put this condition here. Okay. So then what I get here? EFM will basically stay same. Okay. So minus 2n S square J1 plus, okay, I will not rewrite again. That will kind of obvious. Okay. So let me just erase this part and save this. Otherwise, I have a fear that it will unsave. Okay. So here see J1 and J2 both are greater than 0. Okay. So for the FM state, we have J1 plus J2 in the bracket. Okay. And for the FM state, we have J2 minus J1. Right. Okay. So clearly the bracketed term is more positive for the FM case, right?
Yes,
Agree
sir.
or not? So
Yes,
J1
sir. Agree.
plus J2 is greater than J2 minus J1 in such case, right?
Yes, sir.
Which means that here EFM will be less than EAFM, right?
Yes, sir.
Okay. So now you go to Q2. Okay. So here J1 is negative and J2 is positive, right? Okay.
Yes,
So
sir.
if I take care of the sign here, so my EFM will be, so J1 will carry a negative sign. Okay. So this will be, let's say, sorry, minus 2n S square J2 minus J1, right?
Yes, sir.
EAFM will be minus 2n S square. J1 is negative, so this will be J1 plus J2,
Yes, sir.
right?
Yes, sir.
So it is just the opposite of this. So here EFM will have a
Greater energy.
greater energy than EFM, right? Okay.
Yes, sir.
So similarly, if you want for Q3, we can try. Okay. So here J1 is sorry, J1 is negative, right?
Hmm.
And J2 is also
Negative.
negative, right? So now my EFM will be how much? So minus 2n S square, and then there will be minus for both sides. So it will be
Positive.
plus, okay, J1 plus J2, right?
Yes, sir.
And AFM will be minus 2n S square times, so J1 is negative, so it will be J1 minus J2, right?
Hmm.
Okay. So here again you see that FM is always positive,
Yes, sir.
right? But AFM is, so here EFM is always greater than 0, but AFM is negative because J1 is greater than J2, right? In a way.
Yes, sir.
So here we will get again EFM is less than
Yes,
EFM. Okay. Of course, we have to leave this stripped part away because that will your cosine theta of this one part. Okay.
yes, sir.
Okay. So similarly, you can do it for Q4.
Yes, sir.
Okay. So that way, so you are getting whatever we are basically writing here. Okay.
Okay, sir.
Okay. So now come back to this part and then you do it.
Sir, I think in the question J1 mod square will be there.
J1 mod square.
Yes, sir.
Yes. So,
Because in
but,
the
but here the condition is basically J1 mod. Okay. See, there are two ways to solve this thing. Okay. So I will show you one way. Okay. So let's say there is a very easy way. Okay. So what we have done here, when we got the energy, we minimized it, right? So we did del E del theta equals 0, right? Yes or not?
Yes, sir.
Okay. Now, usually when we have such a situation, then we also do something else. What is it? Like, you know, this is kind of an extremum problem, right?
Double derivative.
Yes, you take the double derivative. Okay, so here also you can try that. So all you have to do is that you have to calculate del 2e del theta 2. Okay, so this will come out to be 2n s square j1 cosine of theta plus 4j2 cosine of 2 theta. Okay, or you can also write it 2n s square j1 cosine theta plus 8 j2 cos square theta minus 4j2. Okay, now let's say if we have theta equals 0, so then our del 2e del theta 2 will be j1 plus 4j2 times 2n square. Okay, so now if this has to be stable, so this is
Sir, in
basically
the second line, it should be plus 4j2.
where?
Sir, in the second line, 2n s square j1 cos theta plus 8j2 cos square theta minus, it should be plus 4j2.
Okay, so now if fm is stable, then what we have to do? Basically, this quantity has to be, if we have this, then this will be minus j1 greater than minus 4j2, right? Which means that j1, okay, j1 has to be less than 4j2. Okay, so these are the two conditions that we have got for ferro or antiferro state to be stable. Okay, right? So now what will happen if we go to the other configuration, which is basically my cos theta will be minus j1 by 4j2. Can you try? Anyone?
Yes, sir. In the energy expression, I think it will be minus J1 square by 8J2.
Okay, so what is the value of this? Tell me.
Sir, 2n s square j1 square by 4j2 minus 4j2.
2n,
2n s square
yes.
bracket j1 square by 4j2
And
minus 4j2.
minus 4j2.
Yes, sir.
Okay, so I'm believing on you. Okay, so now if this is stable, okay, so then this bracketed quantity has to be greater than 0, which means that j1 square by 4j2 minus 4j2 has to be greater than 0, right? Which means that j1 square has to be greater than 16j2 square, right?
Yes, sir.
Okay, or we can also write it as mod of j1. Okay, so basically now we have to come to some sort of condition. Okay, so now let's say if okay, let me write it down. Okay, so let's say if j2 is less than 0, okay, right, then the solution will be J1 square has to be, I think, yes. Okay. So let me, I think. So if we take the square root, okay, we'll get a positive and negative sign, right? So let's say mod of J1, okay. So we actually don't know what will be it, but then there will be plus minus 4 J2, right? So, or let's say for the moment just write it this, okay. Now if J2 is less than 0, okay, so then I think what will happen is here our mod J1 will be less than 4 J2, right? Okay, so this is the only solution. Okay, okay, so let's say if J2 is greater than 0, okay, so then let's say mod J2 is greater than 0. So in that case, basically, what will happen? J1's okay. So in that case, basically, J1 square, okay, will be greater than 16 J2 square. So basically, in that case, cos theta will be greater than 1. Okay, so this is not physical actually. Okay, so we have to only consider this situation when J2 is less than 0. Okay, is it clear?
Yes,
So finally, if we combine these two, then we will get to this part. Basically, J2 is less than 0 and J1 is less than 4 J2. Okay, so this will give us helimagnetism. Any question? And no question is clear, right, Tanya?
Yes, sir.
So this basically other part is not physical, so we have to consider the only other option. Okay, so this is one way of showing this thing, and there is another alternative approach which I said. So let's say okay, so here what you can do is that so let's say basically again we'll here start with this fact that this thing has to be less than 1. Okay, anyway, so okay, so that is one condition. Now let's say basically if this helimagnetism has to be preferable over ferro or antiferro, then what we have to have is that this has to be less than this, and this also has to be less than EAFM, right? So we have 3 conditions, okay, right? So we'll be using that. So let's say let's say if we have the another condition, let's say what can I say? So basically we already, let's say, know that our where am I? What to start with actually? Okay, so let's say if I start with this one, this first one, okay. Okay, So they are basically like, I think you do it at home, okay, because it's quite a bit of mathematics in a similar way. Okay, you try it. Okay.
Okay, sir.
Okay, you try it at home. Okay. Okay, so basically this is like relative energy arguments. So that you have to make. Okay. So this phase diagram is clear to everyone, right?
Yes, sir.
Okay. Okay, good.